Yeah, welcome again. As I already mentioned in the previous class, I thoroughly explained about the moment area method. Now I would like to talk about to find out the deflection using conjugate beam method. The method name you observe, what is meant by conjugate beam method. See, the conjugate beam method means whatever the real beam is being given, you have to convert into conjugate beam first. So there is one example is being given directly. You can see that the load is being applied at the center for the cantilever and the E values and I values are being given. This is of course real beam. In the conjugate beam, what will happen? The support conditions will get changed. Wherever fixed support is there, that will become a free, and wherever the free support is there, that will become a fixed. Likewise, for the roller, for hinges, you have to convert first real beam to conjugate beam actually. You can see here how the things are going to change for the conjugate beam supports. This will give you the very clear cut information about the conversions of real beam to conjugate beam. What is that? Case number 1, if you see, there is a pinned connection. Here theta and delta, theta is not going to be 0, but delta is going to be 0 since it's a support, and theta cannot be 0. And whereas in conjugate beam, shear force will not be 0, whereas movement will be 0 because it's a pinned support. Then come to the second case, that is roller. In roller case, in real beam, slope cannot be 0, but delta can be 0 since it is a support. Similar case of first case, shear force will not be 0, whereas movement will be 0 here for the roller case also. Third case, in fixed case, theta, that means slope and deflection both are zeros, whereas shear force and bend moment both are zeros, because it is becoming a free actually. Why? Because wherever the fixed is there, it will become free, and we are only talking about one side support actually. That is, you please understand. It's not that sir already other side free is there, then you have to shift the support condition into fixed. No, I'm only talking about wherever the fixed is there, that is only it is showing here. One side support we are discussing here. So in that way, if it is fixed in a real beam, in a conjugate beam it will become a free actually. Then free beam is there in real case, real beam. Then theta delta will not be 0, theta delta will be there, whereas in conjugate beam it will become fixed actually. So there shear force and bend moment both are not going to be zeros. Then in fifth case actually, theta will not be 0, whereas delta will be 0 since it is an internal pin support, whereas shear force will not be 0, bend moment will be 0. Why? Because internal pin support will become a internal hinge actually when you convert into conjugate beam. Whereas in sixth case, internal roller in a real beam, theta will not be 0, whereas delta will be 0. In conjugate beam, V will not be 0, that means shear force will not be 0, whereas M equals to 0 actually. Then in real beam, theta delta will not be zeros in the internal hinge actually, whereas in conjugate beam it will become an internal support. It will become an internal support. Then there the shear force and movement will not be zeros actually. So I hope you understood the typical concept behind how to convert the real beam to conjugate beam conversions. This method, if you want to apply, this all points you should remember thoroughly. Then only the methodology of conjugate beam method will be understood. You can see some examples of conversions of real beams. There is a one two supported beam is there. One side is hinge, another side is roller. Then it is conjugate beam also similar, roller, hinge and roller only as it is. When it comes to the one side fixed and another side free, now we are converting into another. Wherever the free is there, that side is become fixed. Wherever fixed is there, it is becoming free in the conjugate beam, reverse, vice versa. Then here there is a one overhanging beam having starting support hinge and internal support is as a roller. Then internal support will become a internal hinge actually, and wherever the free is there, that will be becoming a fixed actually, and the hinge support is continuing as it is, whatever you have seen in the real beam, conjugate beam, it will be repeated. Then in case of fixed support and internal hinge and roller is there, wherever fixed is there, it will become free. Wherever internal hinge is, it will become internal roller, and extreme end side roller will be same as it is. Then another last case, fixed internal roller, internal hinge and normal hinge. Then fixed will become free, internal roller will become internal hinge will become internal roller, and hinge will be hinge. So this is the way the thorough understanding about the concept behind real beam to conjugate beam conversions. Then find the deflection at point 1. Example is being given for a one simply supported beam. The total span of the beam is 12 meters, and the reactions already calculated based on the given load, applied load, vertical load, that is 8 kilonewtons, and that is A. At the A, RA we are getting 2 kilonewtons, whereas RB we are getting 6 kilonewtons. So with the data, let me go and check that there is another example also is being given here, but it is a one side overhang is being given, and the values are being given 30 keeps and 20 keeps, and when both RA and RC also is being calculated here. Then there is another example, find the rotation at A with the simply supported beam, but at B there is a one clockwise couple is being given, moment is being given, that is 20 kilo foot actually. Then there is a one more work having fixed and internal hinge as well as load is being applied, and at the end one normal hinge is there. So how to proceed this problem also can be seen. Then there are moment diagrams and equations for maximum deflection. Of course, when we have the simply supported with the uniformly distributed load, having the center deflection, that is delta max, the load is small w, then reactions obviously will get WL by 2 and WL by 2, that is RA and RB. If I give the A and B at the both ends, and then bending moment diagram and bending moment formula is going to be WL square by 8, whereas delta max is 5 into W L to the power of 4 by 384 A. When you have simply supported with the center point load, the reactions are P by 2 and the bending moment diagram is PL by 4, whereas the bending moment deflection value is WL to the power of 3 by 24 EA. Yeah, 24 EA, because it is 16 EA and 48 EA for the cantilever beam. This is for simply supported, WL to the power of WL cube divided by 24 EA. Then you have a one more type of beam, that is simply supported with overhang. So you have a reactions PA by L and P into 1 plus A by L, and you are going to get delta max at the overhang portion, that is at where P is being applied, and the diagram can be seen. The bending moment diagram is going to be minus PA actually, that only just P into A, and both ends bending moments are going to be 0, so only internal support only you will be have, that too especially wherever you have the overhang actually. Then delta max equals to PA square by 3A into capital L by L plus A. That A distance is from outer internal support to overhang portion actually. Then there is a fixed support with the UDL, that is fixed movements are there, that is WL square by 12, and that reactions are WL by 2, WL by 2, and the bending moment diagram is WL to the power of 4, L square by 24. Then you have simply support with the 2 point loads actually. There is a bending moment formula P into A, but delta max is going to be PA by 24 EA into 3 L square minus 4 A square. See, these all formulas are required to calculate the shear force and bending moment, of course deflection values, by using this conjugate beam method actually. Of course, these all values have been calculated using the conventional procedure, that is double integration method, Maclaurin's method. There are plenty of methods to calculate the shear force and slope and deflections for the given beams with different load conditions. And there is a one more cantilever with end point load, but the support condition is being given at the right hand side support, and there is a one more cantilever with uniformly distributed load. The values is being given, and delta max is also is being given PL cube by 3A, whereas for UDL WL to for a 4 by 8A. There is a one big example is being given here, that is fixed beam with 2 point loads with UDL. We have to find out the maximum deflection for the following structure based on previous diagrams. Of course, there is a dead load deflection produced by uniform load is that is delta D1 equals to 5 WL to for a 4 by 384A, that all values can be interpreted, and dead load deflection produced by concentrated loads is so and so. Then total dead load deflection delta dt equals to the delta d1 plus delta d2 equals to 0.32 plus 1.05. So likewise you can calculate the all given deflections. Yeah, with that note I can conclude the lecture 2 and session 2 today. Thank you very much for the listening.